Welcome, polar bears and polar cubs. We're going to talk about electron notations. Now, there are three different electron notations that we're going to learn about. They all will tell you the same thing, but they kind of show it in a different direction. In order to do electron notation, you're going to apply all of these rules. So the off-ball principle, Hund's rule, and Pauli exclusion. You're going to want to have a periodic table that looks something like that. Okay, if you want it, the link for that one is attached to your notes. You'd be able to actually print that one at home if you'd like. Highly recommend. So what does off-balls principle kind of tell us when it comes to exclusion principle or electron notation? Well, what it tells us is that we're going to fill from the highest to the lowest. Scratch that, from the lowest to the highest. Because highest to lowest wouldn't make sense. So you're always going to start with 1s, and then you're going to move your way up. You can't fill 3D before you fill 4s. Okay, all of these show you the same thing. Now, this one, they showed it on the opposite, and they do the diagonal. Okay, so it tells you who you fill and then where you go to next. But off-ball told us that you fill the lowest energy before moving on. Hund's rule. Well, Hun told us that you can only half fill everything before you completely fill it. In other words, everybody's got to get one before anybody can have two. So, for example, A would be correct because 2s is a new orbital. It's got one before it gets two. 2p is incorrect, and it's incorrect because we always do the up arrow before we do the down arrow. C is incorrect because, again, we need an up arrow before we do a down arrow. And D would be correct because we put that second up arrow in the middle instead of putting a down arrow in that first one to the left. Now, what does Pauli exclusion principle say? Pauli exclusion principle tells us that you can't have two electrons with the same spin. You got to have an electron spinning positive and an electron spinning negative. And that's what they all tell us when it comes to electron notation. So how do we do it? Well, for orbital notation, we make these things to signify the electrons that are arrows. Okay. So as you can see, there are some down here already. Okay. So we will start with these. And how do you do it? So the first thing that you want to do is each line represents one orbital. And an orbital, no matter where it's at, can hold two electrons. Hydrogen only has one electron, therefore it gets an up arrow. Helium, on the other hand, has two electrons. It's in the first energy level, so we have 1s, and it has two, so we need to put an up arrow and a down arrow. We start with the basic ones and move on. Next you have is lithium. Lithium is in the second energy level. It's 1 over, so it only has 1 in the second energy level. However, in order to get to 2s, you must have a completely full 1s. It has 3 electrons. Boron has the same kind of deal. You have 1s. It's in the second energy level. However, boron is in the 2p. 2p has 3 orbitals. Boron has 5 electrons. 1, 2, 3, 4, and 5. The half fill before you completely fill works on the orbitals within a sublevel. not all the way across. So I'm going to have you guys try oxygen and then argon. Okay, go ahead and pause it, try them, and then get back to me after the count of 3, 2, and 1. Oxygen has 8 electrons. It's in the 2p. In order to get to the 2p, you have to have a 2s and a 1s before that. So we completely fill that, and we have 4 electrons. We need 4 more, so we need to half fill, and then completely fill. And that would be the electron notation for oxygen. For argon, it is in the 3s. So we need 1s. We need 2s. I'm sorry, it's in the 3p. 2p. 3s. 3p. Argon is the 1, 2, 3, 4, 5, 6th one in 3p. So we need to have 6 in 3p. There's 3, 4, 5, and 6. There's argon. How can you double check that you have the right number of arrows? The atomic number of argon is 18, so you should have 18 arrows. So 2, 4, 6, 8, 10, 12, 14, 16, 18. We are good. So we're going to move on to the second type of notation, and that's electron configuration. Now, what electron configuration does is instead of having the lines and the arrows, now this equals an exponent. So, who is 1s1? So you notice how I said that, 1s1, not 1s to the first or 1s to the second, just 1s1, 1s2. And everyone in the scientific community would know what you're talking about. So, example, 1s1, well, that's hydrogen. 1s2, that's the second element in the first energy level, that would be helium. 1s2, 2s1, that would be lithium. 1s2, 2s2 would be beryllium. 1s2, 2s2, 2p1 is boron. Anybody know who's next? That would be carbon, which would be 1s2, 2s2, 2p2. Now, that is electron configuration notation. I'm going to have you guys try calcium and zinc. Now, with zinc, the D sublevel fills one behind, and that's very important. So go ahead and try calcium and zinc and check them in 3, 2, 1. Calcium is in the 4th energy level. It is 2 over an S. So what I like to do is I like to find where it's at, put that there for S2, and fill in the rest up to it. So that would be 1s2, 2s2, 2p6, 3s2, 3p6. And there's calcium. Zinc is in the third energy level of D, and it is 10 over. So the energy level of D can hold 10. So it becomes 3D10. So I'd fill everything before that. It's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Notice how 4s is in front of 3d. Okay, 3d is one energy level behind. Now, that's the intermediate version of electron configuration. The shortest version is noble gas notation. So, noble gas notation, we're looking at group 18. Okay, we're going to put that into brackets, and then we're going to fill in the rest after it to get to it. Now, an easy way to do this is if you already have the electron configuration notation, look for the last p to the sixth, except for helium, which is 1s2. And then fill in the rest that you had already done. So, for example, sodium. Okay, sodium has, now I'm going to show you this. It would be 1s2, 2s2, 2p6, 3s1. So you're going to go to 2p6. Who's 2p6? Well, that is neon. And then you're going to show the rest after it. So it's going to be 3s1. What about nitrogen? We have 1s2, 2s2, 2p3. Now you might be looking at it and going, Mr. Day, there's not a p to the sixth. That's when you have to go back to 1s2, which is helium. Put it in brackets, and then everything else that followed it. So that is noble gas notation. So I'm going to have you guys go ahead and, again, we're going to try calcium and zinc. I'm going to throw one more in there. I'm going to throw in neon. And we're going to check those in about 3, 2, and 1. So with calcium, we're going to go all the way over on the periodic table, 1 up. That is argon. After argon, I need 4s2. For zinc, I'm going to do the same thing. I'm going to go up one row all the way over to the end. It is also argon. It also has 4s2, but zinc is all the way over in the 3D, and it is 3d10. Finally, it's neon. Now, the reason that I chose neon is that I know a lot of you would do this. You cannot do that. And here's why. Because you have to show the last noble gas it has passed. So it has not passed neon. So therefore, we have to go back up to helium and then show 2s2, 2p6. Now, that is the 3 notations. Okay. On your worksheets, there's going to be ones that have asterisks. Those signify an exception. Okay. So here are the exceptions. Exception number 1 is chromium. And what happens with chromium is what it would look like is this, where you actually have 2 in the 4s and then 4 in 3D. What we've noticed is actually it likes to promote one of the 4s into the 3D, giving you an actual electron configuration for chromium of that. The same thing happens to copper, except for with this one, copper has 9 in the 3D, and it promotes one to fill the 3D. By promoting one, you get a 4s1 and 3D 10. These exceptions, okay, they can be found in the 4th and 9th columns of the D sublevel. So this also happens with molybdenum, Mo. It also happens with silver. Okay, and that's it for our notes.